So I'm Charlie Garayt. I'm a PhD student at High School of Mine and Geosciences. And today I will speak about the simulation of horizontally infinite geomodels with deep generative adversarial networks. And thank you, Florian, for your big introduction to my subject. As we said just before, if you have reality, you want to interpret this reality with geomodel. So a definition from Walvan and Guillaume is that a geomodel is a representation of geometric elements, such as rock unit boundaries, on a scale of meters to kilometers. And me, I see the geomodeling as an inverse problem, which is more usual in geophysical domains. So the forward problem is when you start from a geomodel and you apply an observation process, a forward operator, and you can predict some measurements, and in geology it's a unique solution. The inverse problem is when you start from measurement, from reality, you still know the measurement process, and the issue is that you can have multiple geomodels. Is what we said in other words, when you have 5 geologists with the same measurements, you can have multiple interpretations. And it's more true that you can have some measurements and modelization uncertainties. So me, I see to solve the geomodeling inverse problem, a way to do that is by a Bayesian approach. So the goal is to have a distribution of geomodels consistent with data. So it could be accessible through simulation. The first term of the Bayes equation is the likelihood. It's just very easy to compute. It's just the difference between geomodel that is known and your data. But the big critical point is the distribution of prior geomodels. And in my work, it is solved through deep generative adversarial networks that allow to have a distribution of geomodels. So I will present from a statistical point of view the deep generative adversarial networks. The idea of GAN is to find a transformation from a Gaussian distribution to this geomodel distribution. The GAN, in my case, I just interested in the generator that transforms the Gaussian distribution into a geomodel. To train this GAN, I use a training dataset that comes from Nodi. And also, just here for the visualization purpose, I made a 2-dimensional distribution, a dinosaur distribution. So let's imagine that each point of this dinosaur is a geomodel. So before the training, the GAN just take a Gaussian distribution and didn't produce anything meaningful. It just produced some noise. But the adversarial part of the GAN, the discriminator, will train the generator to produce a meaningful target distribution. So at the end, if the GAN is well trained, it reproduces geomodel. But in my case, I'm not just interested to produce geological models, but to have geological models with lateral extent. And it comes from 2 geological principles. The first principle is the principle of lateral continuity that says that geological domains have a lateral extent, and it could be translated into geomodel properties that you have a horizontal stationarity. You have a horizontal lateral infinite extent, and also the law of superposition that says that you have longer domain at the top of older domains. So it means from geological geomodel properties that you have a vertical non-stationarity. And the way that I solve these 2 properties is with a specific neural network architecture for the GAN generator. Especially, I use deconvolutional layers or a fully convolutional architecture for the generator. The idea of deconvolutional layers is that you have your input and a kernel that will be fixed for each input. So if you have an input and you apply the kernel on your input, you have the output. And if you have an input grid, you still keep the same kernel and you have an output which is applied in the same way on all the location of your input, so it's stationary. The issue with that is that, the first point is that if you increase your input grid size, of course you will increase your output grid size. So it's why I use a fully deconvolutional architecture for the GAN generator. The issue with that is that I want horizontal stationarity, but no vertical stationarity. For example, here I have my input grid, and if I compute two different parts of this input grid with my GAN, you can see that at the top and bottom you have some patch that could be possible come from geological model, but if you complete the grid, this is not a geological model. It's come because the fact that my architecture is completely stationary, and but geomodels are not stationary from vertical point of view. So to solve that, I use a specific grid, a specific input grid structure. I use, of course, first 4 channels that are local noise that allows to have some variability. But I use also a depth grid that is that transforms my input into a non-stationarity from a vertical point of view. And with that, I can just, it allows to have non-stationarity from vertical. So another issue, once this is solved, is that convolutional layers are very local. So if you compute the left part of your of an input grid and the right part of your input grid, you can have 2 geological models that are very nice, but they are not. You have no consistency between them. Of course, the neural network is able to fill the gap, but it means that you have very different geological scenario from your left and your right side of your images. To solve that, I once again change my input grid structure by adding a global noise grid, which on each channel I have the same Gaussian noise everywhere, which allow to have a long range geological consistency. So just to illustrate the impact of the global noise grid, here you have 3 different global noise, and you can see at the top that you have a geomodel that is folded, and at the middle that is flat, and at the bottom a geological model that is another type of fold. Of course, you can have the same behavior as before. If you fix the global noise differently from the left and or the right part of your images, you can mix the folded parameter and have different geological consistency from different parts of your geological model. It could be desired behavior. Another thing is that because if you generate a big input grid, you will have a big output geomodel, but it could lead to some memory problem. So what you can do is just take one specific part of your input grid, generate a geomodel, and you can do the same for another part of your input grid, generate a new patch of your geological model, and if you do that multiple times, you can have a bigger geological model without the need to have a very large memory on your computer. So finally, to go back to the Bayes formula, the goal was to simulate geomodels with consistent with data, and so in this case I have a distribution of prior geomodels, but in fact it is not directly a distribution of geomodels, but more the distribution of input of the latent space of my GANs. So if I write my Bayes formula, it's write with the latent variable of my GAN. But thanks to the GAN, if I just simulate input structural grid, I have just to give it to the GAN and it will produce a geological model. To condition, for the conditioning parts, which could be, because it's just a density where we know all the term, because the first term is just the difference between a geomodel and data, and the last term in this case is just the density of Gaussian, of a multi-dimensional Gaussian. So we can compute all the density and the target density, and we can simulate with MCMC. And in this case, we didn't need to compute all the input width, but only the part of input width that have effect on conditioning data. And also, in this case, the GAN just produce geomodels with no dip. So I add post-GAN rotation to handle dip, to handle geomodel with dip. And the angle is still fine with MCMC. So here it's some example of conditioning data that just represent, for example, a single borehole. And you can see multiple geomodels that are consistent with this conditioning data. And you can see what I found very interesting is that with the same data, you have multiple interpretation of geomodels. And of course, you can have, you can just, once you have your conditioning part of your input structural grid, you can just extend it and have larger geological domains. And here it's another type of conditioning data. It's more complicated with more boreholes, and you can see some geological models that didn't perfectly fit conditioning data in this case, but contrary to database geological methods, it still keep geological consistency. So this method prioritizes geological consistency instead of respecting all the conditioning data. So here, in the same way, you can extend and see larger geological model in the same way. So to conclude, in this work, I consider geomodeling as an inverse problem in a Bayesian framework, which is a new way of thinking geomodeling by a probabilistic approach. And also, I have extended to simulate horizontally infinite geological models that are still consistent with data by transforming geological principle into neural network properties. And finally, it is part of my thesis, and the next steps is to take into account faults and unconformities. So, thank you for attention.
Charlie. Any questions? Yes?
Yeah. Thanks for the great talks. When you apply GANs on different patches, do you get a smooth transition from one patch to the next?
Yes. In fact, I have a smooth transition.
Yeah.
It's because I didn't take just local input structure grid, but also it's what it's in right here, but also neighboring point of my structural grid. And after, so I have a bigger geological model, but I have some border effect, and I cut the edges.
Yeah, so it does consider the borders, the surroundings when it generates the inside the patch.
Yeah. Yes. I have this border effect. It's yes, it's mandatory, but I know this that on this location I have this border effect, and I know how to cut.
Fantastic. Thank you so much.
Thank you.
Good question. Thanks also for the talk, and of course, probabilistic geomodeling is very good. I don't understand. You added, you said noise. You had noise for spatial continuity. I didn't understand this part. So because it's then you use in the GAN training, you use different noise levels as a
yes.
Which is then linked to different structures. Yeah.
In fact, my GAN input is what I write here. It's multi-dimensional grid. You have channels, and you have NZ and NX, which just to extend the geological model. And I have, in this case, 7 specific channels. channels. I have the first 4 channels that allow to have small variations. I have 2 channels that have the same noise everywhere that control yes, the geological consistency, and also last channel to have vertical non-stationarity.
So it's a bit like in non-stationary multi-point Q statistics.
Yes.
Yeah.
I saw that after that it's very similar to MPS to add some non-stationarity.
Yeah. Yeah.
But it's a good way to do that.
Yeah.
Again, really good presentation. You talked about your next steps being looking at faulting and unconformities.
Yes.
If you were speaking to a conference of structural geologists, you've got really intense folding in some of your models. Have you thought about, is your model assuming a constant area, or can you allow for loss laterally? Because I'm squeezing that way to give me my folding, I'm extending in that direction, and material will flow perpendicular to your compression. So you've assumed a constant area. You have got slight thickening at the tips of the folds and thinning on the limbs. But overall, it seems that the area is constant. That's true in a sedimentary basin, but not where you've got a tectonic collision to give you the kind of intense alpine-type deformation that you've shown us.
Yes, it's for just synthetic data, so it's true that it's a fixed area, and I didn't consider some stretching, but I have synthetic, I have no scale in fact, and so it could be have exaggeration on a lateral, so it's less yes, it's less you have a bigger wavelength than could be seen.
So it will make a difference if you're selling this to geothermal energy, water extraction. We don't do oil and gas extraction anymore. Versus putting a tunnel through the Alps, you're asking very different questions of the geology. So the processes, the geological history, is really different. Yes. And the lens that the geologist looks at it through will be very different. So that's just, I'm intrigued.
And in fact, my results also are consequence of my training data set. In my training data set, I have explicitly asking for a flat model and also very folded models. So if you know that your target area is not very folded, maybe you can just take an input data set without this type of folding, which disallow to have this type of results. And the inverted is also true.
Thank you.
Thank you, Charlie.